we go. We've got a trig question here. Let's see how fast we can get this one done. The cross-section of a drain is to be an isosceles trapezium with three sides of a length 2 meters as shown. This one here. Find the angle theta that maximizes the cross-sectional area and find its maximum area. So pretty much we want to find the angle theta that allows for the maximum area of this trapezium. And even there's a couple of ways, but I'm just going to do the way that I guess I did the question. Because I looked, obviously there's solutions to the question, and the difficult part is the first step, but that's what we're going to do. Alrighty, so when you get a question like this, first you want to break it down into what you need to do. So first, find the angle to maximize the cross-sectional area. So I'm guessing we're going to want the area of this shape here. So because it's a trapezium, we know that A is going to be equal to 1/2 A plus B times height. Where A, we're going to assign that to this bottom value here. B, we're going to assign to the top value, and H is going to be the just the height. So when we've got a shape like this, we pretty much want to break it down into its parts. So we've got these, where these are 90-degree angles, and then this will be parallel to the bottom. Yeah, that will be relevant. And then, yeah, that's pretty much all we can do here. We know that this value here is 2. That goes here. That's 2 meters. And then we don't know these end values here, so we're just going to assign these both as x for now, because we know that these are going to have to be the same, because theta on either side is going to be the same. We won't have that there for now though. Alright, then we know we're going to assign A first, so we know we're going to let A equal 2, and we're going to let B equal 2 plus 2x, as we got the 2 here, and we got our 2x values. And then we're going to let H, we don't actually know H yet, but that's what we're going to figure out right now. So we know to find, first we're going to find x. So to find x, we're going to have to use this angle in here. Knowing that, and I'll just redraw this triangle, you know that this is theta, this is a right angle, that is not drawn right. This is a right angle here, and we've got a flat base here. So knowing that pretty much across this entire plane here, this is going to be 180, we can do a few things. We know that this angle in here is therefore going to have to be pi, which is 90 degrees, pi minus theta, because this is 90, so therefore we have 90 left for this side, and we know this angle is theta, so therefore the interior angle here is just going to be pi minus theta, which we will be able to use in a second here, and we know this is 2. So therefore x, using our trigonometric functions, look at us, sorry, Katara, I'm not really going to write that out though. We're going to know that sine pi minus theta, which is the angle in here, is equal to opposite over hypotenuse. So that would be x, because that's opposite, over our hypotenuse, which is 2. Now, just knowing some trigonometric identities, we can already simplify this sine pi minus theta into cos theta, which is equal to x over 2 still. And therefore our x value is going to be equal to 2 cos theta. And we'll later insert that into our value of b here to complete this top part. But the next value we want to find is the height, so that there is h. And then we're going to want to find, using, I think it's called complementary angles, not 100% sure. We'll call this our triangle here, where this is h. Because this value here is theta, and these two lines will be parallel to each other, just like here. We know that this angle here is also theta, so we're going to use that to find we're going to use the same trigonometric identity sine. So we're going to get sine theta is equal to the opposite, which is the height in this case, height, and our hypotenuse, which is 2, and therefore h is equal to 2 sine theta. So we've got our h value here, we've got our a value, now we just need to finalize our b value, which we pretty much have. So b is going to be equal to 2 plus 2x, and x is equal to 2 cos theta, so that'll just be 2 times 2 cos theta, which will give us 4 cos theta. So knowing that, we're going to sub this into our equation here and get 1/2, and then I'm just going to put the h in now, multiplied by sine theta, so multiplied by 2 sine theta, multiplied by 2 sine theta, and then we got our brackets here, which is a plus b. We know a is equal to 2, and then plus b, which is equal to 2 plus 4 cos theta. Alright, we'll further simplify this to this 1/2 and this 2 will cancel out and just become 1. So therefore we'll have sine theta. And then this bracket here can be simplified to 4 plus 4 cos theta. And that's pretty much as far as we want to go for now. It probably could expand it. I'm not sure where that's going to get us though. So I'm just going to stick with the way I did it originally. I don't actually have any working out in front of me. So I'm really hoping that this goes alright. So because after we find the area, so this is pretty much the cross-sectional area of this trapezium in terms of our theta. And we want to find the value of theta that allows us to get the maximum area. So kind of like a quadratic, if you were to just try to picture this, although I have no idea how to sketch this graph, we can allow theta to be there and the area to be here, because we know that this angle, we're going to presume, because looking at this diagram, our value of theta is between 90 and 0. So our value of theta is, it'd be over pi over 2, because that's actually 90. So that's pi over 2 is less than theta, and theta is less than 0. So we're going to assume that there's really no negative angles here. And our graph may look something like this, although it probably doesn't. Let's just pretend to look something like that. The value of theta, where the area is the maximum, will appear here, here, and here. Since we're trying to find pretty much an angle that's between 90, it'll likely be the first one or the second one. But I don't even know what this graph looks like. But what this pretty much represents is that you'll get a value of theta that'll give you the maximum area, and that's what we're trying to find. So like a quadratic, because that's probably what most are used to, you're going to differentiate to find where the gradient is 0, and then that'll give us where our value of theta has, that'll give us the value of theta at that point where the gradient is 0. That will also lead to the maximum area of this equilateral trapezium. So I'm just going to go ahead and differentiate this using the product rule, which if you don't know, let's just give a function f of x. None of these values have been assigned yet. It'll be f of x, which we'll just let sine equal, times the derivative of g of x. So when you have two functions, you can use the product rule that are multiplied by each other, sorry. When you have two functions that are multiplied by each other, you can use this rule. And then you pretty much just swap this around, so then it'll be the derivative of f of x times g of x, just this normal function. So we're going to let sine theta be f of x. So we'll let f of x equal to sine theta. could be done more neatly. We'll just leave it for now. And g of x, we'll let that be equal to 4 plus 4 cos theta. And then we may as well just find the derivative of these right now, since they're pretty short. So then we'll sub it in up here in a second. So the derivative of f of x, which will be the, that's what I should be changing. I should be changing these x's to theta, because our equation isn't in terms of x, it's in terms of theta. The derivative of f of theta, which is the derivative of sine theta, is just equal to cos theta. To solve these equations, you pretty much just want to know your basic derivatives for trigonometric functions, and that'll help you out. And then the derivative of g of theta, which is the derivative of 4 plus 4 cos theta. We know this, the 4 just becomes nothing, but this cos theta becomes negative sine theta, so it'll be 4 times negative sine theta. So it'll be negative 4 sine theta, because this cos theta just turns into a negative sine theta, and the 4 stays. Alrighty, now we're going to sub this into our equation up here, but we're really just going to have these two equal each other. So we're just going to have the derivative of a of theta. So derivative of a of theta, I'm going to need a bit more space for this, I should write it further across. Alrighty, the derivative, it's a bit painful using this device, especially now I've moved on to a different side of the pad. Getting some glitches there. Derivative of a of theta is equal to f of x, which is sine theta. I keep on saying f of x, but it's actually f of theta. I'm going to keep saying that frequently. Maybe I'll get the hang of it soon. Times the derivative of g of theta down here, which is I already stuffed up. No, I haven't. Our derivative, I'll just show this. We got negative 4 sine theta plus the derivative of f of x, which is derivative of f of theta, which is just going to be cos. And then we want this value here, which is just this value here. And then you've got 4 plus 4 cos theta. We're going to see how quick we end up being able to do this, but I wouldn't be surprised if we're not even halfway through this equation yet, considering how slow I'm going. Alrighty, we're going to further simplify this to negative 4 sine squared theta plus 4 cos theta plus 4 cos squared theta. Alright, hopefully that's readable. I'm just kind of expanding here, nothing too much. Alrighty, our next step is trying to simplify this more. So we can see that this sine x, this sine squared theta and this cos squared theta, I kind of already had a method in my head of how to do it. So I'm not sure if I really want to swap it up, because that'd be taking a bit of a risk, so that could be for another time. Actually, I don't think that's not going to work anyways. Alrighty, I'm just going to do how I did it. So we want to pretty much turn this sine squared theta into anything that has cos in it. So we can use our trigonometric identity. So we got sine squared theta plus cos squared theta is equal to 1. So therefore, we got our sine squared theta, not going to write that out just for convenience. Our sine squared theta will be equal to 1 minus cos squared theta, and we can sub that in for our sine x. So I'm just going to do that. Actually, I'll just do that below. So it'll be negative 4, and then we'll have 1 minus cos squared theta, and then the rest of our equation. Starting to get really messy on the y there. And then we're just going to have to further simplify this again. A fair bit of work goes into these ones. We're going to have negative 4 plus 4 cos squared theta, because these negatives can turn into a positive. That's just expanding these brackets here. And then just the rest of our equation again, which we're going to need to simplify yet again. Not helping us out at all. 4 cos squared theta. Alright. I'm getting a call from a mate. I'm going to have to pick that up after this one. Yep. Alright. We'll further simplify this. We'll be able to combine these two ones here to our 8 cos squared theta, and then plus 4 cos theta. It's getting really messy, minus 4. Alright, now that's a fully simplified, derived from this A over here. That's pretty much the fully simplified version from that to this, and now to this. Now we know that this will give us our gradient at any given point. This pretty much represents the gradient and the maximum turning point, or the maximum angle of theta, which is pretty much what we want to find. Or it could be the minimum, we don't actually know yet, but I'm just going to assume it's the maximum, is when our gradient is equal to 0, although our gradient will be equal to 0 anyway, I'm pretty sure. Confused myself there a bit. So we're going to make this equal to 0. Alright, getting messages. Alright, we're going to let our derivative of A equal to 0. It's going to be a pain to simplify. It looks like we're going to factor out 4 first. So we can just divide absolutely everything here by 4 to get 2 cos squared theta plus cos. I'm going to see what we're going to have to do here. Is equal to 0. We have a classic thing where we're going to have to assign variables, and I'm just going to assign u for the sake of it. Alright, so here we have a cos squared theta, and then we have a cos theta. If we were to change this this cos theta value into just a different variable, it would honestly just look like a quadratic. Although it literally is still a quadratic, we're just going to simplify it. Well, we're going to allow cos theta to be assigned to a different variable, just so it looks easier. So we're just going to go u equal cos theta, and no, we're not taking it to the u world, we're just assigning u for who knows what purpose. 2u squared plus u minus 1 is equal to 0. And now you can use a couple methods to simplify this quadratic, but I'm just going to use a method I like to call God method. Has nothing to do with God, but that's just what I thought. Now, I did also find this one up on YouTube. Alright, so it pretty much just allows you to simplify quadratics where there's a coefficient here, and you're not really smart enough to do it yourself. So you just use this method here. So you're at u squared plus u minus 2, so you times the 2 onto this negative 1, and then u, bang, u, and we pretty much just simplify this. So we can see there, this is a plus 2 minus 1, and that'll give you, so u plus 1 and u minus 2. That'll give us this here. But because we've times this to the negative 1, for who knows what reason, I don't actually have the proof, you chuck the 2's here, and then further simplify. Pretty much just simplify it, and then u minus 1. And this will give you your equation up here. There is proof to this, but I don't actually know it. And you don't always, in some cases, you don't even always fully simplify these. You just kind of got to know what to do through experience. So then we know this here will be equal to 2u plus 1. Remember, do not put equals here either, because this is clearly not equal to anything like this. This is just like some working out method to it. Anyways, we'll continue here, and then u minus 1. Pretty sure that should give us our quadratic here. U squared, then we got minus 2u, oh no, sorry. Hold on, I actually might have done this wrong. Plus 1, oh no, I actually did it wrong. Oh, that's too much time taken there already. I really did stuff that up. I wonder if I'll edit that one out. Probably won't. Just gonna have to watch it. Alright, so it's clearly a plus 2 minus 1. I think I even said that but didn't write it. Certainly what I was thinking. Anyways, so then we'll end up with u plus 1. I'm not even sure if this is what I had. And then 2u minus 1. Yeah, this is not what I had. Minus 1 and then plus 1. And then there. That will be our quadratic. That is really sad that I messed that up. We'll have to work that out. Alright, then we get u is equal to 1/2 or u is equal to negative 1. Now we know that u is equal to cos theta. So we're actually approaching the end here. That means cos theta is equal to 1/2 and then u, don't need u, and then we're just going to equate our other one. And then we got cos theta is equal to negative 1. And because our angle, which we established before, is between 90 degrees, which is pi over 2, and 0, as we can see, it's really not meant to go past this spot here. Like, if it's going anywhere up there, I'm honestly concerned, but it's not. Scroll down a bit. Actually, scroll down. Yeah, we'll scroll down a bit. And then, yeah, so therefore we can literally cancel out this. This is not going to be our answer because cos theta equals negative 1 is not within this domain of theta. So then we get our theta is equal to, you take the cos, I want to say cos inverse, but I'm really not 100% sure what you call that one. And then theta is going to be equal to, just knowing your exact values, we know that theta is going to be equal to pi over 3, and that is within our domain, so we're happy. So we got our theta is equal to pi over 3. So we found our first answer to this entire question. Through all that, we still find the angle theta that maximizes the cross-sectional area. We only just found it after all that. And then our last part, and find the maximum area. So we're pretty much just going to sub that back into our equation A, which is this one here, and use this one here. So sub into A. Don't know why I did a lowercase there. Sub into A, and then our next part will be just subbing it in. Yep. We got sine in the final stretch here, sine pi over 3. You can probably just do this yourself. And then cos pi over 3. Knowing your exact values again, we got pi over 3, that'll give us square root 3 over 2. Don't want to get confused here. And then plus 4 times cos pi over 3 is 1 over 2. This will give us square root 3, and then 4 plus 2. I forgot the 2 at the bottom here. So therefore a is equal to square root 3 over 2. I don't know why this is taking so long. For working out, it's always best. And then these will be, this 6 and the 2 will simplify to be 3 squared 3. You're pretty much there, and then that's our answer. A is going to be equal to 3 square root 3 meters squared, and that is when theta is equal to pi over 3. I'm pretty sure that's all we need to do for this question. And yeah, that's it for the question. Game is game.